The last portion of the section is going to be a lot of observations on the tangent graph. We're going to look at the different characteristics in terms of stretches and shrinks, and then we're going to look at what happens when you've got tangents that don't have the same period as the parent function. So starting out with a general tangent function, we want to identify all the stretches, shrinks, and reflections of the following graph. And tangent has the same pieces as all our other trig functions. The number in front represents our vertical stretch or shrink. The number in front of the x is our b value, which is going to tell us the frequency, which helps us find our period. That's your horizontal stretch or shrink. Inside the parentheses then, we've got a horizontal shift, and then the number outside the parentheses is the one that is the vertical shift. Now before we can do that, we need to factor out so that we've got a constant of 1 in front of the x inside the parentheses. So y is equal to 3 times the tangent of 4 times the quantity x plus 1 minus 3. Now that I've pulled that out, I can look at each of the individual pieces. This 3 in front indicates a vertical stretch. Vertical stretch. The 4 in front of that x is going to indicate something horizontal. And this one's going to be a horizontal shrink because the value is larger than 1. Remember that b value is going to tell us the number of cycles we've got to fit within a certain distance. And here we're going to have 4 times as many cycles. So each cycle is going to be compressed horizontally, which means it's going to be smaller. Inside the parentheses, we've got our horizontal shift, which remember is the opposite direction. So this is going to be 1 unit left. And then the back number indicates my vertical shift. So a 3 unit shift, and this one is going to be down 3 units. So those characteristics maintain all the way through our different trig functions. Now, if we look at the tangent graph, there's a couple of observations we can make about this, and this will be at the top of page 67. Tangent of x. We know from the characteristics of tangent, the tangent is the sine over the cosine. And we can determine our characteristics in terms of asymptotes or zeros based off of that. So this is going to tell us 2 important things. The first thing are that the asymptotes are going to occur whenever the denominator is equal to 0. And since the denominator is the cosine, it's going to occur whenever the cosine of x is equal to 0. The second thing, we know our x-intercepts, or our 0 values, occur when the numerator is equal to 0, or in this case, sine. X-intercepts occur when sine of x is equal to 0. So I'll put down my different values on my axis, pi over 2, pi, 3 pi over 2, and 2 pi. And let's start by looking at our asymptotes. The asymptotes occur when cosine of x is equal to 0. And we talked about in the previous section that the cosine values equal 0 when it's in the format pi over 2 plus n pi, where n is any integer. In other words, that's saying the odd pi over 2's is where all the asymptotes are going to occur. So here I'm going to have an asymptote at negative pi over 2, pi over 2, 3 pi over 2, And if I were to continue along, 5 pi over 2. X-intercepts occur when sine is equal to 0. And if you remember back, the zeros are in the format x equals n pi, where n is any integer. So that means at 0 pi I'm going to have an x-intercept, 1 pi I'm going to have an x-intercept, 2 pi, if I were to continue over here to 3 pi, and then over here at negative pi, all x-intercepts. The last piece then is, how is this graph going to look? Since I've got asymptotes on each side of these zeros, I know the graph is going to go against those asymptotes, get closer and closer to them but never touch them. So the question is, like from pi here, am I going to come down or am I going to go up on each side? Or is it going to be some combination of going up on this piece and then coming down over here? Or going down on this side and then coming up as we go to the right? And that's where I can think back to the unit circle. If we looked at tangent in the 4 quadrants of the unit circle, we know in the first quadrant tangent was positive, it was negative in the second quadrant, positive in the third, and negative in the fourth. So if we look at our diagram here for our graph, from here to here, 0 pi to pi over 2, what quadrant does that represent? Well, 0 to 90 degrees represents the first quadrant. And we know tangent has to be positive in this area here, that's the first quadrant. Anything from the y-axis to this vertical asymptote here is going to be the first quadrant. And we know tangent is positive in the first quadrant. So I've got to be greater than 0, which means I'm going to be heading up. The second piece here, this pi over 2 to pi, this area in here represents the second quadrant, anything between pi over 2 and pi. And we know tangent is negative in the second quadrant. So I'm going to come down along the asymptote like that. The third quadrant, tangent is positive. And the third quadrant is represented from pi to 3 pi over 2. So this distance here, everything in between here is the third quadrant. And we know tangent is going to be positive in the third quadrant. And then finally the last piece, 3 pi over 2 to 2 pi, same as 270 degrees to 360 degrees. So this is going to be the fourth quadrant where we're negative. And then as I go along the 2 pi to 5 pi over 2, that's the same thing as the first quadrant due to coterminal angles. So the format that I have of my tangent graph is I've got these exact same swooshes that rise as you go from left to right. We also said that the period for tangent is different than sine and cosine. And we said the period was pi over b for tangent. And the reason for that is we want to know how often does it take to repeat the function. And for tangents, every pi units. If you look at this from asymptote to asymptote, I get the entire graph in, a piece that is negative and a piece that is positive. I see the exact same repeat every pi units. So that's why the period here is pi instead of 2 pi. If I go 2 pi units, I can say I get 2 full cycles in. So that's why. Another way you can justify it. How many cycles do you have between 0 and 2 pi? Well, you get 2 full cycles in. So each period is just pi. How did we find the asymptotes? We looked at where the cosine of theta was equal to 0.